Hello, everybody. Welcome home to the DeTect Talk seminar. So I'm very pleased to see that the room is very full today to come and listen to Tina Dura. So let me introduce our speaker of the day. Tina, you graduated from University of Pennsylvania in 2014 for your PhD. You were actually working on sea level issues. And then you embarked for a first postdoc for 2 years at Ridger University in New Jersey, and then you were honored with an NSF postdoctoral fellow at Humboldt State University in California. And since 2019, you are now a young, bright assistant professor at Virginia Tech, where you've been developing a very original line of work interested in tsunami and paleotsunami. You have a group which is working in sedimentary analysis, including, as you describe on your webpage, diatom-based subduction paleogeodesy. So it's a very specific things. And probably you're going to introduce us to this topic. So I'm going to stop here and let you take over the screen. So I'll stop sharing. And the floor is yours. As usual, please no video and questions through the chat at the end of the talk.
Okay, how does this look? Can you see my screen?
Yep, this is all perfect.
Okay. All right. Well, thank you, Jan, for this invitation to speak in this exciting talk series. Today, I'm going to be discussing my work using the stratigraphic record to extend earthquake and tsunami records over thousands of years to give us a better idea of the hazards that we can expect along these subduction zones. I want to acknowledge some of my collaborators right up front. So I have here listed the Alaska Paleoseismology team that I work with: Rich Briggs, Simon Engelhardt, Peter Hausler, Rich Kaler, Alan Nelson, Rob Witter, among some others. They played a really big part in the research that I will be discussing today. And this is just our field site that I will be highlighting today. But first I want to give kind of an introduction of my work and what we do. So why do we do these paleoseismic studies trying to extend earthquake and tsunami records? Well, our main motivation is that our historical and instrumental records of earthquakes and tsunamis are temporally restricted. In the best case scenario, we might have a few hundred years of quality historical records at a subduction zone. But as we go further back in time, these records are spatially limited, and it's hard to get an idea of how these events really unfolded. And for our instrumental records, we have even shorter, 100 years of some instrumental detection, and then even less time of like really highly detailed instrumental records. So the problem with that is that these short data sets might miss these large subduction zone earthquakes that happen on hundreds of year timescales. And a really good example of that is the Japan 2011 event. Prior to 2011, it was thought that the subduction zone in this area was segmented in such a way that would limit earthquakes to a magnitude 8 in this area. But of course, we had the magnitude 9 earthquake, and it exceeded expectations. And as you can see in this picture here, a lot of the seawalls that were built with these more magnitude 8 earthquakes in mind were overtopped, and you had big issues there, obviously. And it turned out that we actually had geologic records along the coast that showed that earthquakes of this size that happened in 2011 could occur, but those hadn't really made their way into these hazards maps. So I hope that makes the case that we need these geologic records on thousands of year timescales that we can get from sedimentary records to really tell us about the spatial and the temporal variability of events along subduction zones. So how do we get these records along the coast? Well, it really starts, with the earthquake deformation cycle. And that is characterized by a period of interseismic gradual deformation and sudden deformation in the coseismic period. So if we look at this figure here, we have the downgoing oceanic plate. It's stuck against the overriding continental plate in the interseismic period. And this is causing the plate to be compressed and bulge up in some cases on land and then be dragged down offshore. In the coseismic period, we have a sudden release of that strain. Onshore, we can get coseismic subsidence that happens really quickly, and that's on the order of meters. And then offshore, we can get deformation on the order of meters that displaces the ocean floor and can create a tsunami that goes along with it. So this is a cycle. It will repeat itself over and over again. So this can be reflected onshore in the coastal stratigraphic record as a series of relative sea level changes. Of course, to see that in the onshore record, we need to look at low energy depositional environments that are going to be sensitive to relative sea level changes. So if you want to have a 1,000-year-long record, you don't want to look at a rocky coastline, for example. That's not really going to register these changes. So we look at low energy depositional environments that are sensitive to changes in relative sea level and that can capture this kind of up and down that happens during the earthquake deformation cycle. And I just want to point out that this is kind of the simplified version of this, and that we can get some more complex ups and downs and different patterns that occur along subduction zones. But for example, Cascadia behaves like this, where you have interseismic uplift, slow interseismic uplift, and then sudden coseismic subsidence. Okay, so what does this look like then in the stratigraphy, this earthquake deformation cycle? So like I said, we really need to look at places that have this accommodation space that might actually capture these ups and downs of the coastline, which are reflected as relative sea level changes. So we look at low energy depositional environments, and one of the main environments that I look at are these intertidal coastal marshes. So if we look at a coastal marsh here, before coseismic land level change, you might have a nice high marsh peat, an organic soil developing. During an earthquake, you have this sudden dropping of the coastline and coseismic subsidence. Shortly after, you might have a tsunami move in. But what we're really looking for when we look for deformation is this change between this organic soil that was there before the earthquake, and now that the land has dropped down and is being acted upon by tides daily, we get this tidal flat deposit on top. So we have this sudden change in environment if we just ignore the tsunami sand for now. And then in the interseismic period, gradually the land rises again in between earthquakes. So you have your tidal mud that was there after the earthquake, gradually shifting back into a high marsh deposit, showing that earthquake cycle. So this is a core from Cascadia that I think illustrates this really well. We have our pre-earthquake soil here at the bottom. We have our tsunami sand. But as you can see, we have made this jump from a high marsh environment to now an intertidal, tidal flat mud on top, and then gradually changing back into a soil as the land recovers and rises in between earthquakes. So in marshes, you can actually get stratigraphic changes at times that can look similar to these earthquake contacts. So we have these series of criteria that we look at, which are listed here below. So we want these contacts to be very sharp. We want to be able to say that this change occurred very quickly in the coastal environment. We look for a juxtaposition of environments. So in this case, we have this high marsh peat directly overlain by a tidal flat mud. So you would expect, if it was a gradual change, to have gone from a soil slowly into a low marsh, slightly more organic, into a tidal mud. But in this case, we have this jump between environments. So that's what we look for, to show that it happened really suddenly. We want them to be laterally continuous throughout the site. So over hundreds of meters and even kilometers if we can. We want to find that same signal in the stratigraphy. And that rules out localized changes like tidal channel migration, or some reconfiguration of estuary or sand spit, or something that can kind of mimic a sudden sharp contact in a core. It's even better if we can correlate this evidence between regional sites. So once we date it and we can correlate these contacts, it's much more compelling if we can say it happened at a lot of different sites, and that helps rule out these gradual processes that might make these contacts in some cases. And then if we're lucky, we get this tsunami sand in the stratigraphy as well. We don't always get it. At Cascadia, you often find, for example, soil overlain by mud, and you don't see the tsunami. So there are really two different stories going on there. You have the sudden change from soil to mud showing the deformation of the coast, and then you have the sand that is showing the tsunami inundation. If you have both, that's great, and that's really compelling evidence that the coastline deformed in the earthquake because of slip directly offshore, and that you also got a tsunami with that earthquake. So that's going to be a really good indicator of a large subduction zone earthquake right offshore. And then if we look a little in more detail at the tsunami deposit, we can learn a little bit more about the earthquake. So as we know, a tsunami comes in, it kind of scours the beach face, transports the sediment inland. As it loses its inland speed and gains elevation, it's going to slow down, eventually stop, and drop the sediment out of suspension. And so this can add to our story in the stratigraphy. If we can find these tsunami deposits, we often see that they contain this anomalous marine sediment. Obviously, they're bringing a lot of sediment from the beach inland, but they also include sediment from inland because they're going to continue to scour and erode the land as they move inland. They do tend to thin landward and fine landward, and they often contain rip-up clasts of the material they're flowing over. They have this sharp and sometimes eroded lower contact that's gonna show that it was a high energy flow over that environment. And sometimes, if we're lucky, they're coinciding with the land level change I described in the slide before. And so when we have this information, this upward fining sand bed in the stratigraphy, we can sometimes apply inverse models that can use this grain size to kind of back out what the flow speed must have been to transport that sediment. And we can also use forward models that kind of try different offshore slip scenarios to try to replicate what this deposit looks like onshore. So it can tell us a little bit more about the earthquake if we have this tsunami deposit with the stratigraphic evidence. Okay, and as Jan mentioned, I specialize in kind of diatom-based paleoseismology. So how do these diatoms fit into this story? So diatoms are photosynthetic unicellular algae. They inhabit freshwater, brackish, and marine environments. And they're valuable for reconstructing paleoenvironmental changes along the coast because of their preferences for a number of environmental factors. So they're really sensitive to where they like to live. And the ones that, the environmental factors that we employ most in our earthquake and tsunami studies are their different affinities for salinity and substrate. Those are the most useful to us. So if we look at this diagram to the right, we can see a profile here of a tidal marsh. And you can see that we're going to have different diatoms that like to live in these different environments. So in subtidal environments, we often get these round or centric diatoms that kind of float in the water column. They're characteristic of these subtidal environments. As you get higher in the tidal frame, we start to get diatoms that like to live attached to sand grains and kind of a different morphology or shape. And later, as we get into these freshwater or fresh brackish and freshwater environments, the diatoms tend to be a bit smaller and have different morphologies and shapes. And basically, the different species are characteristic of these different environments. So when you look at your sediments down core and isolate the diatoms in those sediments, you can get an idea of what environment those sediments formed in based on what diatoms are living in there. And of course, over time, as we know, we have the coastal evolution, you have sediments aggrading, and those sediments are going to kind of lock in a story of how, in the diatoms of where sea level was in the past with respect to these different locations along this profile. And their diatoms are really important to these paleoseismic studies because they provide this independent test of our interpretations that we're making from the stratigraphy. So if we say we have the sharp contact and went from a high marsh to a tidal flat, oftentimes we know that because we're looking at the diatoms in those sediments and finding that those diatoms like to live in tidal flats or in high marshes versus tidal flats. So it just gives us a more precise interpretation of where those sediments formed. And in some cases, we find sharp contacts and we wonder, is this even intertidal at all? And so diatoms are really useful, obviously, in that, characterizing the overall environment. Okay, so like I just described, we can use this empirical or this relationship that we can observe between where modern microfossil assemblages live and the elevation within the tidal frame. And then we can go down core and interpret or convert these fossil assemblages into quantitative estimates of past relative sea levels. So if you look at the same core we had before an earthquake, we have this nice fresh brackish assemblage of diatoms at the bottom of the core. In the tsunami, we often find this chaotic mixed assemblage that includes offshore and shore diatoms, but can also include freshwater diatoms because the wave is kind of washing inland over so many different environments. But then above that, we have this distinctive change in the diatom assemblage that shows that we've now gone from a high marsh into a tidal flat. And so you can see we have planktonic forms in these diatoms that like to live attached to sand grains. And then diatoms are also really useful in capturing that intermediate environment of the low marsh as you're slowly rising in between earthquakes. And then finally into that high marsh, fresh brackish assemblage as you've now returned back to kind of the pre-earthquake conditions. So what diatoms do is just give us more information then about kind of these, how the environments are changing throughout the earthquake cycle. And then we can use transfer functions that I won't get into in too much detail today as I don't have too much time, but we can use these statistical methods to put a number on the amount of change that occurred during this co-seismic subsidence by employing that modern relationship of diatoms we see today, and then applying that down core and basically putting a number on how much the land must have gone down in the earthquake. Once we have those estimates, we can incorporate them into 3D elastic dislocation models that can basically show if this amount of slip happened onshore, then what, or if this amount of deformation happened onshore, what was the slip like offshore? And the more estimates we have on land of this subsidence, the better that we can constrain these models. If we look in a little bit more detail at the tsunami deposit itself, which is going to give us a different story or different, an added, interpretation to our stratigraphy. We can see that the tsunami deposit often includes anomalous marine diatoms, which can tell us something about the provenance of the sediment of the sand in the tsunami. Again, like I said before, the assemblage is not just composed. It's not usually as simple as just like, wow, there's these marine diatoms that shouldn't be in here. It must be a tsunami. Usually there's a chaotic mix of freshwater, brackish, marine, and you kind of have to look pretty hard to find those anomalous marine diatoms and put that story together. Other times you're lucky and it's really obvious. Often it's a low concentration assemblage. A beach doesn't, dry beach or dunes doesn't include a lot of diatoms. They like to live in wetter environments. So when you have a lot of that sediment transported inland, you might find that your tsunami actually doesn't include a very high concentration of diatoms at all. But that's kind of on also a site-by-site basis. Sometimes it's chock full of diatoms. The high fragmentation is an important characteristic of diatoms and tsunami deposits. They're shown as pristine, really beautiful forms, but often they're fragmented and broken up because they've been transported in with the sand and bumped into sand grains and been fractured in the process. So it shows that high energy flow. And we often see, same with the grain size, where you see the normal grading or upward finding signal, we see the same in the diatoms. So this figure here is from Sawai et al. 2009 of the 2004, the diatom characteristics of the 2004 tsunami in Thailand, I believe. And you can see that this shows the flow or has a mixture of fresh species, beach and subtidal and marine plankton all floating. As you move inland and the sediment starts to drop down and accumulate, you can see that the heavier beach and subtidal species go towards the bottom, and then slowly you go into your freshwater species at the top, which tend to be smaller. So similar to what you see in the grain size, you see the same upward finding in the diatoms there. Okay, so I've had the opportunity to apply these methods around the world. This figure is from a diatom-based paleoseismic study review that I did in 2016. And it kind of covers all the studies that have applied these methods around the world. And the ones that I've highlighted here in white are just the ones that I've had an opportunity to be a part of. So we've had good success with these methods around the world of reconstructing earthquake and tsunami records over thousands of year timescales. Today, I just wanted to highlight some of our work in Alaska because I think it's a really good example of kind of what goes into a paleoseismic study, how microfossils are incorporated, and then how we've then incorporated our work into hazards maps and how we're thinking a kind of bigger picture now of what our work means in the broader picture of Pacific-wide tsunami hazards and earthquake hazards. Okay, so as you can see here, this is Alaska right here. This is the Alaska Aleutian Subduction Zone. And as you can see, we have this remarkable series of earthquakes that have occurred in the 20th century along the Alaska Aleutian Subduction Zone. Here, the rupture areas are shown in pink. And you can see a lot of the subduction zone has ruptured recently, but there are these, boundaries between ruptures. And one of our big questions we wanted to address in our paleoseismic work, which is shown here in these colored dots, and we've been doing for about the past decade, is this 20th century pattern of earthquakes characteristic of what we can expect in Alaska in the future? Or is this just a picture of the recent past and that we shouldn't rely too much on the patterns because as we've seen in other modern earthquakes in Japan, for example, and also in Sumatra, what happens in the future might not necessarily be the same as what has happened in the past. So today, so I've been a part of a little less than half of these studies. The group that I mentioned at the beginning of the talk has, people have been involved in here and there when they can. And so today we're going to focus on Sitkinak Island, which is this island shown here in the red dot. And we targeted this area because of this boundary between the 1938 earthquake and the 1964 earthquake, and questions that remain about the persistence of this possible boundary between earthquakes. So is this a boundary that always exists between ruptures, or is this just something that happened in the recent past, and that can we maybe expect multi-segment ruptures in this area? So we wanted to address that question. Okay, so just to set the stage here, the Alaska Aleutian Subduction Zone is very active compared to, say, Cascadia, that it's so quiet. In Alaska, we have one great earthquake every 13 years or so, and this is based on the historical catalog. We have one magnitude 7 to 8 per year, and 6 magnitude 6 to 7 per year. So it's very active. There's a lot going on. And if we look at the areas, so here's Alaska, here's the peninsula, here's Kodiak Island. If we look at this area in purple, this is where the subduction zone is locked and is accumulating strain and is expected to be able to produce a large earthquake based on the fact that it's over time it's accumulating strain. Whereas these creeping segments, there's a bit of a question of whether you can create larger than magnitude 8.5 earthquakes or so based on their creeping characteristics. So particular concern in this region is the Samiti segment, and that's because tsunami modeling has shown that when you get a large rupture in this area, that first you have a tsunami that's directed towards Alaska, of course, but you also have the orientation of the segment makes tsunamis that are directed towards the California coast. And because the California coast is of such economic importance, has been targeted in studies that are kind of trying to find the earthquake source areas that might create large far-field tsunamis in that area. So the Samiti segment is somewhere that has gotten some attention because of the way it directs tsunamis towards California. The last earthquake was in 1938. It was magnitude 8.3, but it wasn't quite large enough to release all the accumulated strain that has accumulated there. And so it's thought that this area could still produce a large earthquake in the near future. So the USGS had a scenario where they looked at what a Tohoku-Oki type of earthquake occurring on the Samiti segment. So this is the general rupture patch that they used, and found that a magnitude 9.1 would create a 1.2 meter far field tsunami at the ports of Los Angeles and Long Beach in Southern California. and could produce up to $3.4 billion in damage and business interruption in the area. So it would be quite a catastrophic event if we had a rupture in that area. And then, of course, you might have noticed we have the 1964 9.2 earthquake just to the east on the Kodiak segment and beyond. And as I mentioned before, there's been a question about whether this is a persistent boundary to slip, or if perhaps something on the Samiti segment could propagate through this boundary per se and create a multi-segment earthquake that would, increase the impacts of a far-field tsunami in along the west coast of the U.S. So that's something we want to address. And so as we started to conduct these paleoseismic studies, and these are studies on Chirikov Island here by Nelson et al. 2015 that I was a part of, the Sitkinak Island study led by Briggs in 2014, and then ongoing work that we're doing on Sikalitic Island, we were finding that these sharp earthquake contacts that we found at the sites were able to be correlated across this boundary, especially evidence we found for an earthquake in 1788. So is this evidence that there are multi-segment earthquakes in this area if you look further back in time beyond just these historical earthquake patterns? So spoiler alert, we think that there can be multi-segment earthquakes in this area, but I want to show you kind of how we arrived at that conclusion. And for that, I'm going to focus on the Sitkinak Island study that's right at this boundary between the 1938 and 1964 earthquakes, which was, we targeted it because it's in this area where we might be able to pick up some multi-segment type earthquakes if we can find evidence that correlates with sites to the east and the west. Okay, so Sitkinak Island, like I mentioned, it's in a perfect location because of the location between the 1938 and 1964 ruptures. It's also oriented in such a way, so here's the island here, and this is north. It's oriented in such a way where the low energy depositional environments that we identified on satellite imagery are facing the south towards the trench and are in a good location to catch tsunamis. And also these low energy environments are in a great position to catch land level change because they're in the, in the proximity of the subduction zone that we would expect deformation. And we have the right environments that could catch that deformation. So we have these intertidal marshes. So we targeted this island. And so this is the team, and these are basically the folks that I mentioned on the first slide. And we all kind of bring something different to the table. Everyone has a geomorphology background. We have, people who also can excel in bear protection. So you can see not on Sitkinak, but on other islands that we've gone to, there are large brown bears. And we have to actually carry weapons to make sure that we're safe from that. And we have people who are, focus on kind of the geomorph and surveying element of the studies. We have sea level experts and kind of big picture guys. We all bring something a little bit different to the table that really makes these studies rewarding, and I think makes our interpretations stronger. So our goals for Sitkinak were to reconstruct the land level change and tsunami inundation history of the island using the stratigraphic record. And you can see most of us, some people have shovels, some people have coring devices. So we do our stratigraphic investigation. We want to try to characterize a slip during past ruptures based on the results that we get from kind of what the island is doing in the earthquake cycle, going up or down. And then can we use this evidence to evaluate the persistence of the proposed segment boundary between the 1964 and 1938 earthquakes? And if needed, do we need to update the hazard maps? Do we need to say that this is not a persistent boundary and that we can possibly expect multi-segment earthquakes? Okay, but Sitkinak is remote and difficult to get to, so we have to keep that in mind. So I just wanted to show a video of us landing on Sitkinak. So prior to our trip, we had identified this old runway. It used to be used to land C-130s, so quite big airplanes, but it hasn't in quite a long time. This was back in World War II and a bit after. Lately, it's just used as a Coast Guard refueling station. There's nothing else there really. There's a ranch, the remnants of a ranch, but really it's uninhabited. So we thought we were landing on this really large runway. It turns out we landed on this tiny little sliver of runway. It's basically just a gravel road. And you can see one airplane has landed ahead of us with some of our crew and gear, and we're coming in behind them. And we were warned by the pilot that it was quite windy the day that we flew in, and he told us it would be a very sporty landing. And so here we go. This is, you can see a bit of the old Coast Guard station and some of the refueling station. But that's me in the front there, pretty nervous. So I just wanted to show this to highlight that it is not easy to get to these places, and we often wonder what we're thinking, but we've always made it there safe. So that's our arrival in the Sitkanak. And okay, so here is the runway that you just saw. We landed coming in this direction, kind of going to the southwest. And our main field site turned out to be here in the south of the island, like we hoped, kind of facing the trench. And here's Camelback Ridge, which is just a good geographic point to remember, so we can look at future photos and kind of orient ourselves. So originally we had thought maybe these lowlands would be good candidates to look at in our study, but it turns out that there's very fast currents that come through the middle of this island every day. So this was all quite mixed up and not very useful. So we ended up making our main field site to the west of Camelback Ridge. You can see this more protected intertidal marsh area that was really good for coring. And we also did a bit of reconnaissance here, but didn't really take that too far when we're working up more cores from this area now. But today we're going to focus on this main field site. So this is us. Here's Camelback Ridge right here. And here we are flying in towards the south. And then we do a big loop and turn around, come back. And so here we are coming back, flying north, and here's Camelback Ridge, and we're looking down on the field site here. Okay, so we have identified where we want to core. So here is Camelback Ridge again, and here's the area where we got a lot of our land level change evidence cores. And here we are standing on Camelback Ridge looking down onto that same area. So our strategy when we get to site really is to do these coast perpendicular and parallel transects, so we can look at the stratigraphy and try to correlate stratigraphic evidence across those. A lot of it involves just coring leapfrog. So here's one team looking at gouge cores, and the next team describing another one. So as many as we can get, the more the better, so we can try to correlate these contacts throughout the site. If we're lucky, we have these nice outcrops. So you can see this in this outcrop, we have these changes between peats to muds to peats to muds. So we're starting to see a really interesting story developing. And this is an outcrop that's just around in this area here of this island and this low energy depositional environment. And then a big component of our studies is surveying to make sure that we tie everything into where mean sea level is today. We need to know that to then interpret how sea level changed in the past as the island went up and down in the earthquake deformation cycle. So that's a big component of our studies, and we always survey every core location. And in this case on Sitkanak, we also had to install a tide gauge that we left up during the time we were there because there's no tide gauge here. And so we had to establish that mean sea level datum ourselves. So in all this coring, we started to notice, you can see a little better in the outcrop, but you can also see in this gouge core, these interesting changes between these muds and peats at Sitkanak. And so here's a short video of kind of the coring, because a lot of times it's hard for people to visualize how this all works. So here's a picture, a video of 2 meter Peter, Hausler here, and Andy Kemp. And they are coring, and we're actually coring a bit inland here, where we found some tsunami evidence, and the island we were just looking at is just a bit here, a few hundred meters away in the distance. But basically we just use these hand-powered gouge cores, In this case, there's a Russian attached to it, which is this coring device that has a chamber that closes around it, where you can recover sediment without any dragging or less compaction. But it's quite an effort to get these cores recovered. And you can see that the height difference between the two can sometimes create a little bit of an angle there on the core. All right, so it's basically a chamber you put in the ground, you turn it, close around the sediment, and then you open it. And you can see that in this case, we found a couple of sand beds in the peat and even a large tephra that often helps us correlate our stratigraphy. Okay, so that core was quite a bit, mouse went. Okay, anyway, the core was quite a bit inland. If you looked kind of to the north of Transect 2 is where we just saw that video. And a lot of the work that we focused on was, there it is, here in Transect 3, where we had that land level change story. And because of these outcrops that we were able to find on the edges of this island, you can see that we were able to correlate just based on looking at these notches, these are peat that's sticking out over hundreds of meters. And then we would clean periodically along this wall to make sure we're still looking at the same stratigraphy. But we were able to correlate these changes in stratigraphy over large distances of this island. So another important part of the study is to characterize the modern environments. So this is just a marsh that kind of was fringing that lower environment. And we want to characterize these modern environments to see what microfossils are living in today in the modern environment, and then be able to relate that down core. So we do that both in marsh transects and also in beach transects. This is going to help us with the land level change story, and this is going to help us argue that the provenance of the sand beds that we're seeing in the cores were from the beach. Okay, so then once we've kind of characterized the stratigraphy, we want to sample it. So we get these PVC pipes and sample the stratigraphy. We then take rootlets, seeds, any kind of organic material we can to date. We use radiocarbon dating to date these peats and create a chronology of when these sudden changes in our core occurred. We then run grain size. That helps with tsunamis and also just reconstructing past environments. We often run loss on ignition to look at the organic content. And we do our diatom analysis. Okay, so this is all those cores that were shown in the map from Transect 1, 2, and 3. And I'm not going to focus too much on 1 and 2 because they contain a slightly different story. But I want to focus on Transect 3, where we found evidence of land level change, just basically that change between those peats and those muds. And I'm going to focus in on this core here, WS5. And so you can see that we were able to, we had these CT scans that identified these sudden changes between muds and peats and between peats and muds. So we had changes that went in both directions, where we had the sharp contacts between a peat and a mud. So basically where you see an arrow that indicates where an arrow pointing up, we think we see evidence of coseismic uplift. And where the arrow is pointing down, we think we see evidence of coseismic subsidence. So we have this mixed record of uplift and subsidence occurring at the same site, which I'll get into a little bit more in a second. So we wanted to look at the microfossils, obviously, across these contacts. So this is just a summary of what I found in the modern intertidal environment, where we had brackish and marine, and typical brackish and marine species in the lower marsh, all the way up to our freshwater species. And this is what I saw down core. And so we were able to look at each of these contacts and look at the microfossils. First, they were dated to around 1,000 years BP, around 600 BP, around between 300 and 500 calendar years BP. And then we think we see the 1788 earthquake and the 1964 earthquake in our stratigraphy. So we looked at the diatoms across those contacts and found that in the oldest contact, we saw a change from a tidal flat to a high marsh to a tidal flat in the next contact. And I should say the lower contact, we think we see uplift. The next one we see subsidence. The following one, we go from a tidal flat to a high marsh showing uplift. The next one was a low marsh to a high marsh showing uplift. And then 1964 seemed to show a low marsh going to a tidal flat, indicating subsidence. So it was an interesting story where wasn't it just as straightforward as repeated coseismic subsidence? We actually saw this signal of mixed coseismic subsidence and uplift. So how is that possible? Just want to check my time. Okay. So our model that we came up with is that here's Sitkinak Island on the lateral edge of a rupture shown in this schematic. So when ruptures stop at Sitkinak, you might have this subsidence trough that wraps around the edge of the rupture and creates subsidence at the island. And this is something that may have occurred in 1964, where the rupture stopped right at the island, and then we see coseismic subsidence in our stratigraphy. And when you have this slip propagating through and not stopping right at the island, that would create uplift at this position. So when ruptures propagate through Sitkinak, you can get coseismic uplift, which is similar to what we saw in that 1788 contact where the diatoms indicated uplift. So our model then is that when ruptures stop right at the island, like in 64 shown here, you have subsidence, and when they propagate through, you have uplift. So that's kind of shown in 64 and 1788. So as you go back in time, we can see that in the past, we've had some ruptures that stopped at the island and others that propagated through. And you can tell that based on the direction of the land level change that's preserved in the stratigraphy. So this suggests to us that this segment boundary is not persistent. You don't have the same type of behavior, deformation behavior occurring at the island every single time, but it depends on what where the rupture stops, basically, with respect to the island. And this is supported by the evidence on either side of the site at Chirkov and at Siklitic that shows that 1788 rupture at these two sites, indicating that that rupture did propagate through Sitkinak Island. Okay, so now that we have that information, the new hazard maps that will come out will incorporate the possibility for multi-segment ruptures, which I think is, it's nice when your paleoseismic work can make its way into those types of maps. And what we've been thinking about more now is, can we use these results to inform earthquake and tsunami modeling and learn more about potential impacts of future events? So we had the Sapphire source modeled, but now that we know that we might have multi-segment earthquakes, what can we expect then in Southern California from this? So we've been considering this, this possibility for multi-segment earthquakes and doing something similar to the Sapphire modeling, and also considering compounding hazards. So as we move a decade, 50 years, 100 years into the future, how is sea level rise actually going to compound the effects of tsunamis in Southern California that might come from this part of the subduction zone? And this work is in revision right now. So what we did is we looked at the ports of Los Angeles and Long Beach, similar to Sapphire, but in our modeling, we use multi-segment earthquakes, which created this distribution of tsunamis here between about 1/4 meter and over 2 meters. But then we also considered, what if the tsunamis hit high tide versus low tide? So we combined our blue histogram with the green tidal histogram and created this red distribution of possible tsunami heights in from multi-segment earthquakes along the Kodiak and Yosemite segments. So we have this more realistic distribution of what might occur at the ports depending on the tidal stage, because that's a big important for what the tsunami heights could be. So we found that we could get, just today, we could get tsunamis over 2 meters at the ports of Los Angeles and Long Beach from these multi-segment earthquakes. And so, like I said, we wanted to consider multi-segment, compounding hazards. I'm running out of time a little, so I have to rush. But so we combined our tsunami modeling with sea level projections. And we looked at both kind of low emission scenario sea level projections and higher emission scenario sea level projections. So in worst cases, by 2100, in the lower emissions, we have 1.5 meters of sea level rise. And in the higher emissions, we have about 2.5 meters of sea level rise. And so we incorporated the sea level rise into our modeling so that our tsunamis would hit in the future based on this rise in sea level, and it obviously would increase the height of tsunamis that might occur there. So if you look at these compounding impacts, this graph here shows the earthquake magnitude that has a 50-50 chance of exceeding a defined flood height. So in this first panel, it's 1 meter flood height, and as a function of time. So as we're going into the future from the year, okay, here we go, from the year 2000 all the way to 2100, as you can see today, using that distribution of possible maximum nearshore tsunami heights that we modeled, today you would need around a magnitude 9.1 to get a tsunami of about a meter at the ports of Los Angeles and Long Beach. But as you go into the future, that magnitude drops significantly. So by 2080, in these higher emissions sea level scenarios, that sea level rise at the ports of Los Angeles and Long Beach is going to allow even smaller magnitude, 8 earthquakes, to exceed this 1 meter flood height. And that's basically the highest that has been observed at the ports of Los Angeles and Long Beach ever historically. So by 2100, magnitude 8 could make that flood height. And then if we look at higher flood heights, 1.5 meters, that's similar to what Saffir did, which is kind of an extreme scenario. Today you need a magnitude 9.4 based on our modeling. As you go into the future, you could have something as small as I meant to say 9.4 if I didn't. In the future, you can get as small as a magnitude 8.4, creating that same 1.5 meter flood height. So something that was causing the $3.4 billion of damage can happen much more frequently. An 8.4 is 6 times more likely than a 9.4. So you have these earthquakes that are more likely to occur, creating the same amount of damage as these very rare earthquakes. So that's kind of how we're expanding on our paleoseismic work and looking at kind of broader implications of these events. Okay, so I want to wrap it up there and just thank my collaborators again. Here we are enjoying a nice beer at the end of the day on the island, and some other collaborators that have contributed sea level projections, earthquake modeling, tsunami modeling, and sea level reconstructions that have all contributed to the work I've done. And that's it. Thank you.
Thank you, Tina. That was a very exciting talk. So the chat box is open. Please feel free to start typing your questions, and Tina will take your questions and answer your questions.
Let's see if I can bring up the chat box.
Yeah.
Okay, I can see the chat box.
Yeah, it always take a few seconds for people to start typing. All right, here it is.
Okay. Okay, so we have a question from Ronald Bergman, who asks, who says that Shannon and Hamilton and Hawks et al. Suggest that earthquakes in Alaska and Cascadia were preceded by a short period of pre-seismic relative land level subsidence. Do you see evidence of that anywhere? I have not, and I think knowing those authors personally, I think there's still a lot of questions around that evidence and whether it's actually showing that signal. And they do discuss in those papers the possibility of different processes that might create mixing. So we're seeing lately in a lot of contacts at Cascadia that there is a little bit of mixing across the contact that might be contributing to a signal like that. You know, I'll always look out for it and be hopeful that there could be something like that, but so far I haven't really seen compelling evidence for that. How could we identify, this is Linking Jiao, how could we identify the deposit by a tsunami or cyclone? As we know, big cyclones could also bring this sand into the sea and deposit it on the land. Very good question. I get it often, and I have the same question myself all the time. And we always have the same question in the field and discuss it. So yeah, it's very hard. It's going to be very hard to distinguish a sandbed deposited by a tsunami from a sandbed deposited from a storm surge for example, my work in Chile, we can often exclude the possibility of storm surges because they don't have very large hurricanes striking the coast there. They do have big coastal lows that can create erosion, but we don't see a lot of evidence of storm deposition there. But in other places like Alaska, we do have big enough storms that can bring quite a bit of sand inland. We always have to consider that possibility. So one of the ways that's really that you can exclude the possibility of a storm is if you have deformation with the tsunami. So storms don't cause land level change. You wouldn't expect widespread change from a high marsh to tidal mud with your tsunami deposit. Or with a storm deposit, excuse me. So that's one way. So that's why I really like land level change, and I don't like to rely too much on just anomalous sand beds. But there's no smoking gun that I know of yet that just tells you for sure that it's not a storm. So you always have to consider that possibility. Also, the recurrence interval between storms in Alaska, for example, is much shorter than what you would expect from huge tsunamis. So that's another indicator that you're probably looking at tsunamis if you have these really large gaps in the sand beds. Okay. Jeremy Maurer had a question about deposition rates. Since you mentioned during the interseismic period, the land level can rise. How does this affect your ability to interpret the sedimentation results? So we have often in the past and still focus a lot on those coseismic contacts because they're the most straightforward to interpret. And we're thinking a lot more about trying to get that interseismic period dialed in more. So far it's been difficult. A lot of the times the interseismic sediment is tidal mud, so it's hard to find material to date in that. So you can't really get the chronology, that time. And there's so much variability in the sedimentation rate. And for example, in Alaska, in some places, especially in the 1964 rupture area, that you can get really, really fast, like meters of post-earthquake sedimentation. And then in other places, like in Chile, it's really, really slow. And so the interseismic has been really hard to dial down. And so we've often focused on that coseismic contact, but we're working on getting that interseismic better quantified because it will help a lot with locking models and things like that. Okay, Robert Leeper. Have plans to install GPS monitoring equipment on Kodiak. Okay, there's definitely GPS stations installed on Kodiak and on Chirikov, and I hope I'm not wrong, but I think there's one on Sitkinak. So we have a good, you can find that data online, and we have a good idea of what the islands are doing now. And then another question was, do you see a decrease or increase in diatom fragmentation in samples analyzed moving inland? Because I focus a lot on the deformation part of the story, I don't know of a site where I've really looked at the fragmentation percentage in a systematic way going inland. But I imagine that, and I'm thinking of other papers that people have observed that as you go inland, the energy is decreased and the preservation is better as you go inland. I follow, do you see any transient deformation evidence shortly after earthquakes? So that's a really good question. There's this, the interseismic is a big question people have, and then we also think a lot about the post-seismic. I personally haven't encountered really strong post-seismic signal in the samples I've looked at above the contact, but for example, Yuki Sawai in Japan has used diatoms to look at the post-seismic signal in Hokkaido and has seen that recovery happen quite quickly after that sharp contact. I've seen a more typical gradual change that doesn't seem to have, go quicker right after the contact than above, getting closer to when you'd expect things to be recovered. But I have seen both in the SIGCONNECT study and also in Chile, this mixed uplift and subsidence signal. And so, but overall, it's kind of, seems to have been accommodated over those hundreds of years equally and not really, concentrated in any part of that interseismic period. Are there any other processes that could cause such a sharp? Yes, definitely. And that's something that tried to touch on in the intro, just saying that there are other processes in a marsh. For example, if you have tidal channel migration, you can get a sudden, mud that's deposited in an area where peat was forming before, and other, reconfigurations of estuaries. But those processes seem to be, or tend to be localized, and that's why we try to correlate our evidence over hundreds of meters and even over multiple sites to try to rule out those types of changes. And that's also why, like on Sitkinak Island, we try to stay away from places, where we know there's a lot of activity, and this channel probably migrated throughout this central area. And when you look at the stratigraphy here, it's a complete mess. Whereas you look over here and you can tell that things were a lot more stable over the time period that these sediments were deposited. In core descriptions in Transect 3, which you showed, there are abrupt stratigraphic changes without tsunami deposits. How do you think the relationship between crustal deformation and tsunamis? So that's a good question, and something, I could have done a 2-hour talk on all this. So we have this Sitkinak story, where is it? Okay. And that's another reason we went back. So I'm gonna try and move this. That second time in 2018 is that we have this land level change story lower down, and you can see these are all tied to core tops are tied to elevation. So we have these lower cores on that island that showed this land level change story, and in many cases didn't include a tsunami, and some it did. And then as you went higher in the transect and further inland, you have this different story of more of a continuous peat interrupted by tsunami sedimentation. And we think, and these are much older. So it seems that at some point, the island was, so that's maybe not the best. Okay, this is better. So where we see the tsunami, the older tsunami stories around here, and where we see the more land level change story are in the lower cores here. So we hypothesize that at some point in the past, in this older story where you have these peats forming, that maybe this long spit here was configured differently to the point where tsunamis could get inland and deposit these sand beds. And then later on, the island evolved and the spit developed and kind of closed it off and turned off that tsunami story, and basically just captured those ups and downs with the deformation. We're still trying to work that out, but there is this kind of 2 different stories happening at the same time on Sitkinak. And then finally, how long does it take for a new diatom species to settle down after abrupt change of environment? How does it impact your ecosystem? So that's a really good question, and something that we've thought about. And I don't want to say that. So we have a study in Cascadia that where we had a marsh that had been diked and basically closed off from tides to change it into pasture land. And they took those dikes out and restored tidal hydrology. And we were able to monitor the microfossils before and after they did that. And the diatoms responded within weeks. We basically sampled within a week, I think, of tidal hydrology being restored, and then every 2 weeks subsequently. And the diatoms responded really quickly to that change in tidal hydrology. And other microfossils like forams, which we looked at, took a bit longer to reflect those changes. And that's just one site. So I don't want to say forams do not work. Please don't misinterpret. But it did show that diatoms do respond quickly, and that's also supported by other studies that show they respond quickly. They have a higher a shorter reproductive cycle, so they can, you know, have a new bloom relatively quickly. And so that gives us confidence that we aren't missing some post-seismic signal that occurs in the weeks and months after an earthquake. The diatoms should pick that up because they should respond quick enough.
All right, thank you, Tina. I think this is time. Thank you very much for your talk and answering all the questions. So next week we'll stay within marine stuff. We'll have Hector Pereira talking about high resolution bathymetry and active tectonics. So please come join us next week. And if you want to listen at details or re-listen to the talk, it will be online very soon. Thank you very much. Bye-bye, everybody.
Thank you.